For my project, I created a BangBang thermostat controller. My eventual goal is to actually attach this to my apartment thermostat so that this controller can turn the knob on that thermostat. This is beyond the scope of this project, but here's an overview of my eventual plan. First, 3D print some gears, grippers, and a housing for components, then attach it to the old thermostat in my apartment. Connect a Wi-Fi chip to Arduino for remote control and remote scheduling. Then get a rotary encoder or a brushed DC motor for rotational position sensing. Then implement a PID controller to turn the knob to the right position, which corresponds to the user's desired temperature. My basic circuit setup involves a temperature sensor, a potentiometer for user input of desired temperature, a motor controller, and a motor to represent how I would actuate the thermostat knob. To start out, I wanted to experiment with getting temperature readings and getting user input on temperature. So I used multipliers to make sure the voltage outputs of the potentiometer and the temp sensor were in the right range to correspond to degrees Fahrenheit. So here you can see my experiment. I'm fiddling with the potentiometer while measuring the temperature, and you can see that when I move the potentiometer, it actually impacts the temperature reading. And I think this is because the circuits aren't isolated. They're both on the same ground. As I increased the resistance of the potentiometer, the temperature would drop. So I had to add a correction factor that just looks at the voltage coming from the potentiometer. I also implemented a rudimentary Kalman filter that doesn't actually take into account any plant dynamics. It just smooths out the signal based on the knowledge that there is significant noise in the measurement. In this plot, the blue is the raw temperature reading, the green is the Kalman filter, and the orange is the offset used, which is also actually used in the Kalman filter. The yellow is the potentiometer response. After this experiment, I tried implementing BangBang control with the motor based on temperature readings and the user desired temperature input. Here you can see the conditional statements that implement BangBang control with a hysteresis deadband plus a timer on the motor control while it's in the deadband. Lastly, here's just a quick look at the function that actually controls the motor. Basically, positive motor speed values make it go forwards, negative ones make it go back, which could correspond to hot and cold, respectively. Generally, the code worked, but there were a handful of problems. In this clip, I'm trying to keep the temperature in the deadband, but the temperature measurements are so noisy that the motor just spins back and forth, despite the deadband being about 6 degrees wide. I think this is due mostly to the back EMF induced by the motor, which causes these obvious voltage spikes that are far beyond the deadband. You can see that even my Kalman filter can't completely attenuate this, because when there are so many peaks, it just brings up the average. In the next iteration of this project, I think I would actually try to isolate the circuits a lot better, because I think a lot of the issues surround the voltages of each component impacting one another. I do have some parting thoughts. First, the system is way too noisy and responsive, but increasing the deadband too much will make the system basically useless. I think the solution is better circuit isolation. In the future, the BangBang controller will probably just trigger the PID controller to rotate the knob to the correct position. And lastly, a fast settling time in that knob position would actually be very undesirable, just because I don't want my room heating up super fast. And also, percent overshoot has to be 0 because I don't want my room getting way too hot. So these are kind of totally different priorities from normal control theory, which I thought was interesting.